Introduction. Today, Roy and his brother Ajit are walking in a park. There are so many games and rides in the park to enjoy. Ajit insists Roy for a ride on seesaw. Roy replies positively and walks towards seesaw. When they both sat on seesaw, then seesaw was not balanced. Then Roy pushes himself towards forward on the seat. Now the seesaw is balanced and they enjoy the ride. After the ride, Ajit asked Roy that how was he able to balance the seesaw. Then Roy replied him that seesaw works on the principle of torque. When two equal and opposite forces acts on the ends of a surface, only then rotational motion is produced, otherwise not. In our daily life, we see so many examples of rotational motion. So, let's study more about this system of particles and rotational motion. Objectives. At the end of this lesson, you will be able to define rotational motion, define center of mass, calculate motion of center of mass, derive linear momentum of a system of particles, calculate vector product and angular velocity, define torque and angular momentum, know equilibrium of a rigid body, calculate moment of inertia, analyze work done and angular momentum in rotation, understand rolling motion. Definition. Rotational motion is common in our daily life. The wheels, spinning top, blades of a fan, merry-go-round all perform rotational motion. A body is said to perform a pure rotational motion if every particle in the body moves in a circular path, such that the center of these circles lie on a single straight line called as the axis of rotation. Center of mass. Center of mass point of a body is defined as a point where the whole mass of body can be assumed to be concentrated. It is an imaginary point. The whole body can be replaced by its center of mass. Position of center of mass of a body. The moment of mass of the center of mass point of a body about a fixed point is equal to the sum of the moments of masses of all its mass particles about that fixed point. If the body is made up of n mass particles, then the position vector of the center of mass is given by r vector is equal to m1 r1 vector plus m2 r2 vector plus so on till mn rn vector by m1 plus m2 plus so on till mn. On summarizing above relation, we get r vector is equal to summation from I is equal to 1 to n of mi into ri vector by summation from I is equal to 1 to n of mi. The center of mass point of a body made up of two mass particles always lie on the line joining them. Motion of center of mass. The equation of motion of the center of mass is as follows. V vector is equal to dr vector by dt, multiplying both sides by m and differentiating with respect to time t. We get mdv vector by dt is equal to md square r vector by dt square. This equation can be written as mdv vector by dt is equal to f vector. Working in terms of the center of mass of the system, we ignore the internal forces internal motion, and internal structure. We need to take into account only the external forces acting on the system. Relation between the momentum of the system and the momentum of center of mass of the system. mv vector is equal to m1v1 vector plus m2v2 vector plus so on till mnvn vector. This equation can be written as mv vector is equal to summation from I is equal to 1 to n of product of mi and vi vector. We conclude that the total momentum of the system is the same as the momentum of the center of mass. Relation between the force acting on the center of mass and the forces acting on the individual particles of the system. ma vector is equal to m1a1 vector plus m2a2 vector plus so on till mnan vector. By applying Newton's second law of motion in the above equation, we get F vector is equal to F1 vector plus F2 vector plus so on till Fn vector. We conclude that the force acting on the center of mass is equal to the vector sum of the forces acting on the individual particles of the system. Linear momentum of a system of particles. If F vector is the net external force acting on this system, m is the mass of the system, and v vector is the velocity of the center of mass of the system, then the equation of motion of center of mass is F vector is equal to d by dt of product of m and v vector. If no external force acts on this system, then the F vector will be equal to 0. By putting the value of F vector in above equation, we get d by dt of product of m and v vector is equal to 0. This equation can be written as mv vector is equal to constant. We conclude that if no external force acts on the system, then the total momentum of the system is constant. This is the law of conservation of momentum. When value of m is constant, then v vector is also equal to constant. We can conclude that if no external force acts on a system, then its center of mass moves uniformly in a straight line. Vector product of two vectors. A vector product of two vectors p and q is a vector r such that magnitude of r is equal to pq sine theta, where p and q are magnitudes of p and q, and theta is the angle between the two vectors. R is perpendicular to the plane containing p and q. If we curl up the fingers of right hand around a line perpendicular to the plane of the vectors p and q, and if the fingers are curled up in the direction from p to q, then the stretched thumb points in the direction of r. Angular velocity and its relation with linear velocity. The rate of change of angular displacement is known as angular velocity. If a rotating body turns through an angle delta theta in time delta t, then its angular velocity omega is given by omega is equal to limit delta t tends to 0 of delta theta upon delta t, which is equal to d theta by dt. The angular velocity of a rotating body is a vector quantity, and it acts parallel to axis of rotation, and its sense is given by right-hand rule. All particles of the body rotate with the same angular velocity, but their speeds are different. Thus, the linear velocity v of a particle moving in a circular path of radius r is given by v is equal to r into omega. Angular acceleration. If the angular speed of a rotating body changes with time, it has some angular acceleration. The angular acceleration is the rate of change of angular velocity. The angular acceleration is given by alpha, which is equal to limit delta t tends to 0 of delta omega upon delta t, which is equal to d omega by dt. The angular acceleration is a vector quantity. It is directed along the axis in the same direction as omega when the angular velocity is increasing, but opposite to omega when it is decreasing. Torque and angular momentum. When a force acts upon a body, then a straight line drawn from the point of application of the force in the direction of force is called the line of action of the force. Torque about an axis of rotation is equal to the product of the force and the perpendicular distance of the line of action of the force from the axis of rotation. It is denoted by tau. Tau vector is equal to product of F vector and R vector. Angular momentum. If a body is rotating about an axis, then the sum of the moments of the linear moments of all the particles about the given axis is called the angular momentum of the body about that axis. Let's take an example. Consider a body consisting of n mass particles of masses m1, m2 and so on till mn. Let the particles be rotating about an axis with a constant velocity omega, and let r1, r2 till rn be the perpendicular distances from the mass particle to the axis. Moment of this force about the axis of rotation is equal to F into r. By putting value of force, we get m into r into alpha into r, which is equal to m into r square into alpha. Torque acting on the body is given by tau is equal to m1 into r1 square into alpha 1 plus m2 into r2 square into alpha 2 plus and so on till mn into rn square into alpha n. This equation can be written as tau is equal to summation from I is equal to 1 to n of products of mi and ri square into alpha. This gives tau is equal to I alpha. If alpha is equal to 1 radian per second square, then I is equal to tau. Equilibrium of a rigid body. There are two essential conditions for a rigid body to be in equilibrium are follows. The vector sum of the forces acting on the body must be 0. The net torque acting on the body must be 0. There are three types of equilibrium, and they are as follows. Number 1. Stable equilibrium. If the body is displaced a little and a torque is removed, then body will return back to its original stable state. Number 2. Unstable equilibrium. If the body is displaced a little and a torque is removed, then body will not retain its original state. Number 3. Neutral equilibrium. Potential energy of the body remains constant. Moment of inertia. Moment of inertia of a body about its axis of rotation is defined as the product of its mass and the square of the perpendicular distance of the body from its axis of rotation. It is denoted by I. I is equal to mr square. The moment of inertia of the rigid body will be equal to the sum of moments of inertia of the particles. Its expression is given by I is equal to summation from I is equal to 1 to n of products of mi and ri square. Radius of gyration of a rigid body about its axis of rotation is defined as the perpendicular distance of the point where the mass of the whole body can be assumed to be concentrated from the axis. It is denoted by K. Its expression is given by I is equal to mk square, which is equal to summation from I is equal to 1 to n of product of mi and ri square. Theorem of perpendicular and parallel axes. Theorem of perpendicular axis states that moment of inertia of a plane about an axis perpendicular to its plane is equal to the sum of its moments of inertia about the two mutually perpendicular axes lying in its plane. Iz is equal to Ix plus Iy. Theorem of parallel axis states that the moment of inertia of a body about any axis is equal to the sum of the moment of inertia about a parallel axis through its center of mass and the product of the mass of the body and the square of the perpendicular distance between the two axes. I is equal to ICM plus MH square. Work done in rotation. Let a body rotate about an axis passing through O when a turning force F is applied at a point P. If the tangential and radial components of the force F are Ft and Fr respectively, then work done for a small angular displacement is given by dW is equal to Ft dot ds. Put the values of ds in above equation. dW is equal to FTR d theta. Here R is equal to OP. Replacing the above equation in terms of tau, we get dW is equal to tau d theta. By integrating on both sides, we get work done is equal to product of tau and theta. Thus, the work done is given by the product of the torque with the angular displacement in radians. Angular momentum in rotation. Let us consider one particle of the rotating body of mass m1, which is moving with a linear speed v1 in a circular path of radius r1. The angular momentum of a particle about an axis is defined as the moment of its linear momentum. Hence, angular momentum of particle p1 is given by L1 is equal to m1 r1 square omega. The total angular momentum of the rotating body is given by L is equal to L1 plus L2 plus so on till Ln. By putting the value of L into above equation, we get is equal to m1 r1 square omega plus m2 r2 square omega plus so on till mn rn square omega. Thus, we get the result. L is equal to I omega. Rolling motion. Motion of a body across a surface combined with rotational motion of the body so that the point on the body in contact with the surface is instantaneously at rest. We have the following three laws of rotational motion. Number 1. A body continues to revolve about an axis with constant angular velocity unless acted upon by some torque. Number 2. The rate of change of angular momentum is equal to the torque applied. Number 3. For every torque acting on a body, there is an equal and opposite torque acting on some other body. Rotational kinetic energy. Total kinetic energy of the rotating rigid body about a given axis is equal to the sum of the kinetic energies of all the constituent particles about that axis. Rotational kinetic energy is equal to half m1 r1 square omega square plus half m2 r2 square omega square plus so on till half mn rn square omega square. On summarizing this equation, we get rotational kinetic energy is equal to half summation of product of m and r square multiply by omega square. But we know that summation of mr square is equal to moment of inertia of the rigid body about the given axis. Therefore, rotational kinetic energy is equal to half I omega square. The moment of inertia of a rigid body about a given axis is numerically equal to the twice its rotational kinetic energy when it is rotating with unit angular velocity. Did you know? The position of the center of mass depends upon the shape of the body. For a given shape, it depends upon the distribution of mass in the body. It is closer to the heavier part of the body. In a uniform gravitational field, the center of mass and the center of gravity coincide. The vector sum of all the external torques acting on the rigid body must be 0. Summary. Let us summarize what we have learnt. Center of mass point of a body is defined as a point where the whole mass of body can be assumed to be concentrated. The center of mass point of a body made up of two mass particles always lies on the line joining them. The force acting on the center of mass is equal to the vector sum of the forces acting on the individual particle of the system. If no external force acts on the system, then the total momentum of the system is constant. This is the law of conservation of momentum. The angular velocity of a rotating body is a vector quantity and it acts parallel to the axis of rotation, and its sense is given by right-hand rule. Torque about an axis of rotation is equal to the product of the force and the perpendicular distance of the line of action of the force from the axis of the rotation. The moment of inertia of the rigid body will be equal to the sum of the moments of inertia of the particles.